No kidding. Makes it easy on me. Only got 5 sets of eyes to choose from.
That makes it harder for me because now I gotta answer all your questions.
You're right. Better call your friends and tell them to get in here quick. Okay. We left off last week talking about EAS reactions predominantly. But I want to show you this video quickly, which is a video by Veritasium on YouTube. Have you guys heard of Veritasium before?
I've seen this video.
You've seen this exact one?
Yeah.
I
watch Veritasium.
I love him. Pretty much as soon as he releases a video,
Yeah.
I'm watching it. But he did something wrong, and I'm not here to throw shade, but I am here to point it out. I don't know what just happened. Jacob. Here we go. Let's see how loud it gets.
And as a result, the carbons in the benzene ring become slightly positively charged, and the chlorines slightly negatively charged. Now, if you heat up tetrachlorobenzene with sodium hydroxide, one of the negative hydroxide ions will want to bind to one of the slightly positively charged carbons in the benzene ring. And to do that, it forces...
Did you see that?
Mm-hmm.
Did you see the way the hydroxide replaced the chlorine? Bumper car stars. Bumper car stars.
Carbons in the benzene ring become slightly positively charged, and the chlorines slightly negatively charged.
Electron.
Now,
Yeah,
if you heat
that's
up
an electron pair.
tetrachlorobenzene
It's a
with
bonding
sodium
pair.
hydroxide,
Look what
one of
happens
the
to
negative
it.
hydroxide ions will want to bind to one of the slightly positively charged carbons in the benzene ring. And to do that, it forces out the chlorine atom, taking its place.
Did they leave?
No.
This creates trichlorophenol,
What
or
the
TCP,
hell?
a key ingredient in making the herbicide.
That is not the mechanism. Veritasium is suggesting, and again, I love this guy. He's great. He even invented his own little chemical symbol for his show. He's indicating there that the electron pair between C and Cl stays with the C. And that oxygen is not donating electrons to form the bond. And that chlorine is not keeping the electrons. But I want to remind you guys, when a bond breaks, today's going to be very mechanism heavy, so bond breaks, electrons go to the partial negative. He even said chlorine is partial negative, carbon is partial positive. That's where the attraction is coming from. When a bond forms, where do the electrons come from? The negative. It has electrons to share. It decides whether to make a bond or not. For those of you just coming on, I want to show this one more time to show you what a bad mechanism looks like. This is double-sided, by the way, this sheet.
Negatively charged.
Oh.
Now, if you heat up tetrachlorobenzene with sodium hydroxide,
This is
one
a
of the
bad
negative
mechanism.
hydroxide ions will want to bind to one of the slightly positively charged carbons in the benzene ring. And to do that, it forces out...
Bad, bad, bad. I watched it over and over. My partner thought I was crazy. I am. And did you notice what happened to the ring in there? It stayed the same. That ring representing aromaticity stayed the same. I'm here to tell you that that is not how this reaction occurs. Deal? Okay. Now, what type of reaction do you think this is? It is a substitution reaction, but it's not SN1 and it's not SN2, despite how it maybe would look on there. And I'm saying that it's not because it's on an aromatic ring. Aromatic rings cannot do SN1 and they cannot do SN2. So is this electrophilic aromatic substitution, EAS, or is this nucleophilic aromatic substitution, NAS? Nucleophilic? Anybody agree or disagree? Yeah? What's the nucleophile? The hydroxide. And the ring is being substituted with that nucleophile. Hydroxide is donating electrons to the ring, despite how the video might show it. And so we're saying that we are substituting the aromatic ring with a nucleophile, NAS. So last week when we were building this table up here, we were looking at all of the different substituents, and then we described their role in EAS reactions. That's the big picture. We're going to come back in and look more at EAS reactions. But I want to give you guys first the generic EAS mechanism. It's going to look generic at first so that we can just apply it directly to more specific mechanisms later. Remember that I like to show my mechanisms kind of step by step, but I encourage you to show them fully sequentially if you like it that way, if it makes sense to you that way. The EAS mechanism is how many steps? Just 2. It's the longest 2 steps you'll ever see. And I should preface, some mechanisms have precursor steps where we activate the electrophile, so we'll show that. But the generic mechanism is that the benzene ring, no circle, can't have a circle here because we actually need to use those electrons. The benzene ring will react with an electrophile. I'm going to abbreviate that as E+. And like I said, many of our mechanisms will have a precursor step or several steps to making this electrophile activated. Electrons from the ring attack E+. I do want to make it clear, when I draw this intermediate, I have 2 choices. The top carbon or the bottom carbon is capable of using those electrons to attack the electrophile. So I could have placed the electrophile at either of those positions. I also want to make this clear. There's a hydrogen at both of these carbons. That's not changing at this step. So if it clarifies it more, draw in that hydrogen as a reminder that it is an sp3 carbon right now. This other carbon also has a hydrogen, and because of that, it's sp2 carbocation. Notice the conservation of charge. True or false, this carbocation is conjugated. Conjugated means that it is in an uninterrupted series of p orbitals, or an uninterrupted series of sp2 or sp atoms. sp2, 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 sp2. It is conjugated. We would describe this as an allylic carbocation. You could argue it's a diallylic carbocation, but it is adjacent to a pi bond, which means that this structure does not just exist in this resonance form, but this structure exists in these 3 resonance forms. This is what we call the sigma complex. I'm not quite sure why they picked that name for it. I would have called it the EAS intermediate. But it's called the sigma complex, perhaps because it's no longer aromatic. And so it's broken due to a new sigma bond that's been made. Again, not quite sure. In the generic mechanism, where there are no substituents, there are always 3 resonance forms, but that can actually increase. Anybody brave enough to add electron arrows here to show the formation of the middle, and to the middle to show the formation of the end? Just showing electron pushing for the resonance. 1 arrow each. We can split it up. Jacob's got one of them. Yourself? Great. Perfect, Jacob, that's it. You got it. Good. Great work. Carbon double bond breaks. Carbon double bond forms. Electrons break towards the partial negative. Well, which of these 2 carbons is more negative? Not clear. Bonds form from the more negative. It's definitely clear that when this bond forms, it's forming because of this carbon, not because of the carbocation. Electrons need to flow towards the positive charge. Okay, that's step 1. Step 2 is that whichever resonance form you want to show, since we drew this resonance form last, that's the resonance form I'll show. All resonance forms are the same molecule, so it does not matter which resonance form you actually pick. And then I've got my carbocation on the top here. There is a base. It depends on what reaction you are seeing. But there is a base that uses a lone pair of electrons or a negative charge to bind to the hydrogen. The CH bond breaks towards the partial negative. Carbon owns those electrons, and it uses them to satisfy the aromatic ring. It reforms aromaticity. So, what has been substituted? What did I miss? Everything. The hydrogen has been substituted. It is an aryl hydrogen that is substituted in EAS every single time. It's an aryl hydrogen. So I want to show you what our EAS reactions are. Today I want to actually give you a kind of a dynamic flow chart similar to how we've done our OCHEM1 reactions. So these are the EAS reactions that you will need to be familiar with. We've got 6 different reactions, but 2 of them, the Friedel-Crafts acylation and alkylation, there are different reagents that you can use. So I'm going to try and demonstrate that for us. Since we've got 6, we can try to do kind of a hexagon structure, but I do want you to keep in mind that for 2 of them, we're going to have 2 different routes showing different reagents. Okay. First one, bromination. Br2 with catalyst iron 3 bromide. Can you tell me a byproduct formed here? FeBr3 is a catalyst, so it will never be consumed. HBr, hydrobromic acid, hydrogen bromide, whatever you'd like to call it. That is a byproduct here. Good. In terms of the base in the last step of the reaction, Br minus, correct? Br minus is our base. That's how we get HBr as a byproduct. Next to that, we'll show chlorination. Cl2 with aluminum trichloride catalyst. Byproduct in this reaction, HCl. The base in the final step of the mechanism, what takes the hydrogen? Chloride. Beautiful. I do want you guys to be familiar with the names beyond just their reagents, so please feel free to add in these names. I know some of you don't like this graphic design, so you restructure it in a way that works for you to have just a list, and you could do it just like this. From here, we're going to look at the Friedel-Crafts alkylation. And this is where we have two different reagents. And this is how I plan on demonstrating that. Two different reagents that get us to the same product. Does that make sense? I'm starting from the same material. I'm ending with the same product. I'm just going a different route. Yeah? One of the routes that we can take is an alkyl halide. Perhaps an alkyl chloride works best. Although, to be fair, these catalyst metals are fairly interchangeable. So you could use alkyl chloride, you could use alkyl bromide, and aluminum trichloride. Or you use some sort of alkene and acid. And that's an abbreviated alkene. I do want to make that clear. We're going to kind of abbreviate it again a little bit more in a second. We'll show examples here. Notice that the alkene and acid is a similar reaction to one you've already seen. That is similar to the acid-catalyzed hydration mechanism. If water was present, we would add H and OH. So this reaction has a carbocation intermediate. And the fact that it runs parallel to this gives us the same product, tells us that this also likely has a carbocation intermediate. And the final product that we get, we've got this R group attached. I've got to be careful because I did this example. And so to be precise, this is the R group that actually attaches. Carbocation forms in the most substituted position. So that most substituted position is bonded to the CH3 and the R. So to make this line up, maybe my R here should be also bonded like this, a CH3 and R. Regardless, it's a generic example. What you're getting out of this reaction is an alkyl group on your ring. And so this is named Friedel-Crafts alkylation. Although, if you were to pick any of those words to remember, just remember alkylation. What do you think?
Sorry, what is alkyl? What's an alkyl group?
So it's like alkyl halide. It's that carbon bonded to a
Like the one in
a
between.
halogen. We say that your alkyl groups are methyl, ethyl, propyl, isopropyl, butyl, isobutyl, sec-butyl, terp-butyl.
Is it based on alkane?
Yes and no, but predominantly alkane. Okay, our next reaction is also a set of reactions. This one is Friedel-Crafts acylation, or if you remember anything, this reaction is called acylation. A similar way to the bromination, chlorination, and alkylation that we've already seen is that you can take an acid halide, specifically we'll use an acid chloride, and run it with aluminum trichloride as a catalyst. There's 4 reactions on the board already. Aluminum trichloride is a catalyst for 3 of them. Makes it a little bit easier to remember what to use. In a similar way, you could also take this functional group and react it with your aromatic ring to add on an acyl group. Can you tell me that functional group on the left? Not a ketone. Not an ester. Nothing thio, that would be sulfur. It is an anhydride. Its legal name is acid anhydride because you take 2 equivalences of carboxylic acids, merge them, less a molecule of water. So if you added H2O, you could make 2 carboxylic acids. This is an acid anhydride. That's where it gets its name. So as far as I know, Friedel-Crafts is named after the acid halide with aluminum trichloride. I'm not sure that Friedel-Crafts has their name connected to the anhydride, but you will see a reaction in your homework where you actually use the acid anhydride instead. And I'm gonna have to move my title for this because it's in the way of my next reaction.
Is it 1 or 2 more?
2 more. Can you give me a byproduct? So sorry, I should take a step back. Can you give me a byproduct of the Friedel-Crafts alkylation with this top reagent, the alkyl halide? HCl. Because the hydrogen, again, goes missing from the ring, and the hydrogen is gone. What about here? Can you give me a byproduct in this reaction?
Hydrogen gas?
Nope. Nope. Because there's actually no chlorine. Sorry, I'm pointing at this one.
Oh, sorry, I thought you were pointing at the green.
Actually, the green is another HCl. So this one gives a byproduct of HCl. This one gives a byproduct of HCl. What about the alkene with the acid? Is there a byproduct? Hydrogen gas? Mm-mm. Recognize that the alkene is going from CH2 to CH3. That's actually the very first step. The alkene protonates itself from the acid, creates a carbocation. The ring attacks the carbocation, and then some base takes hydrogen off again. Or if there is no base, H plus falls off, which means this is a catalyst, and there is no byproduct. You could think of it as moving around of the hydrogen. The hydrogen from the ring becomes a hydrogen of the alkene, which is actually now just an alkane. No byproduct. byproduct in this reaction with the acid anhydride? How much of the anhydride gets put on during the acylation? One of the carbonyls, both of the carbonyls, both carbonyls, and the anhydride linkage oxygen? Just one of the carbonyls, which means something else is happening to the other carbonyl and the oxygen linkage. What's the base? Well, that is a carboxylate, the conjugate base of a carboxylic acid. So the byproduct, can you get to it already? The byproduct is a carboxylic acid. That's where the hydrogen goes. The hydrogen from the ring gets removed and brought into the carboxylic acid. Very fun. Okay. I'm not doing so hot on my hexagon shape, and Friedel Crafts is to blame for that, I believe. Next, though, we have nitration. Our reagents here are concentrated nitric acid and concentrated sulfuric acid. Which of these reagents do you think is the catalyst?
The acid.
They're both acids.
Sulfuric.
Yeah, since you're trying to put NO2 onto a ring, the HNO3 is going to be consumed in some way. By the way, I want to show you what NO2 looks like, but I'm going to encourage you, when you're allowed to summarize it as NO2. So if I were to rewrite this, it would be NO2 coming from the right-hand side. But it's important to know the structure of the nitro group because we are going to rely on the resonance that it can provide. Can you name a byproduct in this reaction? Not H2, it's not HO, H2O. The hydrogen from nitric acid is gone, and the hydrogen from the ring is gone, and one of the three oxygens from the ring is gone. So our byproduct here is water.
Sulfuric acid.
Sulfuric acid is a catalyst, not being consumed.
Is it used and then it comes back?
Yeah, just like all catalysts. Catalysts change the mechanism. Catalysts create a different mechanism for a reaction to run through. And if they're good catalysts, that lowers the activation barrier for the reaction by providing a new route. Sulfonation doesn't need to be plural, I apologize. This is the process of adding a sulfonyl group. And we can write this two different ways. We can write SO3 with H2SO4. But one way that you will see this written is it will just be sulfuric acid and it will say fuming. Do you know what the fumes are that sit over concentrated sulfuric acid? It's water and sodium trioxide, sulfur trioxide. This is sulfur trioxide. That is the electrophile in the reaction. Or perhaps after it gets protonated, it's the electrophile. Sulfuric acid is again a catalyst in the sulfonation reaction. So you'll see it for me as SO3H2SO4. You may see it in other places as fuming H2SO4.
So it's dehydrated sulfuric acid?
It's not so much dehydrated as it is decomposed, because the water is still present in fuming sulfuric acid. SO3 is not dehydrated sulfuric acid. It's just sulfur trioxide. Any byproducts in this reaction? You're just moving the hydrogen again. No byproducts. Just like this one down here, where the alkene in alkylation, we have no byproducts. The hydrogen from the ring is now actually a part of the SO3H group, the sulfonyl group. Okay, so sulfuric acid, very strong acid. It actually gives the hydrogen to SO3, and it gives us bisulfite, HSO3, not bisulfite, HSO3 plus. That is the electrophile. HSO4 minus then acts as the base in the last step to take the hydrogen from the ring and regenerates our catalyst, sulfuric acid. Questions on your 6 EAS reactions?
In the acylation, do the R groups have to be the same?
For the anhydride?
Yeah.
Great question. We describe anhydrides as being symmetric if the R groups do match, and asymmetric if the R groups do not match. Do you think it would be better, more logical, to have a symmetric anhydride for that reaction or an asymmetric anhydride?
Symmetric.
Correct.
Want the right product.
If you don't want to get a mixture of both R groups on there. So a symmetric anhydride makes the most sense. In your active problem, it's actually a cyclic anhydride, which means that it opens and the carboxylic acid byproduct is still attached, right? Because if R here connects to R here, then this R still connects to this R, and the carboxylic acid is attached. Cool stuff. All right. So here is where I want us to dig into a little bit more behind the directing effects before we look at the mechanisms, yeah?
Are cyclic reactions there harder to start? Does it take more energy to break it apart than the chain?
Nope.
Same amount?
Just depends on the compound. It just depends on the compound, yeah. There's not like an intrinsic challenge to having a ring. All right. I want you guys to look at the longer side, not the side with the short answer stuff at the bottom. At the top, I've got this diagram for you. Of course, my bonds are in a different place, but you know that those are just resonance forms, so it doesn't really matter where the bonds are. Electron donating groups. These have lone pairs, except for, and I uploaded this onto Canvas, it's underneath the written homework. That's where you'll find it. These typically have lone pairs. These lone pairs can be donated into the ring. I started to show you this last week, but today we're going to look more at that directing effect. If a lone pair comes in, a lone pair needs to come out. I'm breaking the octet at this carbon here. And there's only one bond that it can break. It's this double bond that it's already in. And it can only break in one direction, to the other carbon. So the resonance form that we can predict here is that this electron withdrawing group, electron donating group, creates this resonance form. So on your document, you will need to fill in what? Just the charge. I'm saving you a little bit of the legwork of drawing all these rings, just so that you can visualize it better and we can go through it a little bit faster. What is the relationship between this position and the electron withdrawing group? Ortho. I'm just going to put that in parentheses. That lone pair is sitting ortho. All right, here is another resonance form. Lone pair in, lone pair out. I actually like this form the most because you get all of these parallel double lines. What is the relationship between the lone pair and the electron donating group? Para. And one more. Lone pair in, lone pair out. I've been making a mistake this whole way through. I apologize. You guys know what mistake I've been making? Sorry? There should be a positive charge on this electron donating group.
Wouldn't it be withdrawing then?
No, it donated electrons to the ring. If you donate electrons, you don't have them anymore. Positive charge for you.
The donating group gave electrons to the ring.
That's right.
That's
why the group is called donating.
Yeah, you're positive on the. Okay, I thought you were saying
What-
on the ring.
What is the relationship of this lone pair in the last resonance form to the electron donating group? Ortho. Both ortho positions get a lone pair, and the para position gets a lone pair, which means that we can think of this ring like this. Oops, not with the double bond there. There is partial negative character at the positions ortho and para to the electron donating group. So the electron donating group is an ortho-para director, and it makes the ring a better nucleophile. That's most relevant to us in EAS reactions. Sorry, it's only relevant to us in EAS reactions. So what I'm putting down here is that you can think of this ring as being this. This is approximately equal to partial negative character. We have this diagram where we say the ring is a nucleophile. Okay, but what if it's not just the ring? These groups impact the nucleophilic character of the ring. They tell the ring, you should attack from these positions relative to me. That's going to lower the energy of activation only when the ring attacks from one of these positions. So here is where we get this idea, and this I think is on the back side of your sheet. Electron donating groups make positions ortho-para better. Nucleophilic sites and then the second part we're actually going to have to prove next. This is just one of the proofs that we can use as to why electron donating groups are ortho-para directors. So now we need to get into the mechanisms more. Do you guys still need these reactions? Can I take them down?
I need them.
Yeah? All right. We can... I think I'll just bring this back then later. So we'll go in the order we started in. We'll start with bromination. And I'm going to have to clarify the specifics of the mechanisms for bromination. And then those generic two steps will come in a little bit later. In bromination, the first step, activation of electrophile. I'm going to draw out everything in the reaction just to keep it all present. But if something is not going to be reacting, then we won't show it doing something in that step. It'll still be there though.
Do we just need a sheet to write all this down?
No, the sheet will come in handy. In fact, this is the first reaction at the top of your sheet. But you don't necessarily have to copy this down on the sheet. Activation of the electrophile. What we see here is bromine act as a Lewis base and forms a bond with iron, the Lewis acid. Think about how electrons were just shared between neutral species. What charges do you expect to see now? Positive where? On the bromine. Bromine shared electrons. Now it has less electrons of its own. Iron accepted electrons. Now it has more electrons of its own. Now a lot of people look at that and they say the most electrophilic bromine is the bromine with the positive charge. But actually that bromine doesn't want to accept more electrons from something else. It wants to get its own electrons back. This bromine is the electrophile. If it helps, you can actually show what's going on closer to the iron. It's got a lot going on at the moment. So for some other reagent to get close to the iron and try bonding to that Br+, not going to be helpful. But if Br+ can take its electrons back from the other bromine, well, that means the neutral bromine is actually available to be attacked.
Are you showing us multiple mechanisms?
I'm sorry?
Multiple mechanisms?
We'll be going through the mechanisms for bromination, chlorination, alkylation, and acylation. And NAS. Nucleophilic attack, sometimes called an addition step, because it truly is addition followed by elimination, giving us net substitution. In this step, I have to show all of the electrons on my aromatic ring, because this is where it plays a role. The group on my ring, is it electron donating or electron withdrawing?
Withdrawing.
Withdrawing? Donating? Donating? Does it have a lone pair adjacent to the ring that the ring can borrow? Yes. Then this is an electron donating group, which means I can expect the ring to attack from the positions ortho or para to the ring. I will get both. We're only going to show one. So at this point, and I know I don't mean to hide this from you, at this point I'm going to clarify that the reaction we're looking at is the formation of one of two structural isomers. We're showing the formation just of the structural isomer on the left But the structural isomer on the right also forms, where the oxygen has directed the new substituent ortho to itself and para to itself. It doesn't matter which ortho side, because it's achiral. Those ortho positions are equivalent. So from here, I want to show the formation of the ortho group. I need to use the electrons that the ortho carbon has at its disposal. I'm going to redraw my electrons so they match up with what you have on your sheet, which just means I'm drawing from a different resonance form. Trust me, they all work together. It doesn't really matter where you start from. I'm just trying to make it set up well for your sheet. The ortho carbon attacks, bonds to bromine. The Br-Br bond breaks, alleviates the positive charge on that bromine. Where is the positive charge now? The positive charge is on the carbon, exactly. And I'm going to draw my FeBr3 with the Br bonded to it. I'm going to draw this up a little ways because I've got some sigma complex intermediates to draw here. All right, take a look at your sheet. What? Well, that's right, I haven't done it yet. Take a look at your sheet. This is what you're starting with. So feel free to use this as a template to copy it down into your notes, or feel free to copy it into here. That positive charge, it's on the carbon on the top right position. I just want to make it clear, the positive charge is not in an ortho or para position. That's not what we're looking for. The ring attacked from an ortho position. But let's look at what happens when the ring has attacked from here. Let's look at what happens to that positive charge. Pi bonds move up. I get another resonance form. Feel free to track along with what you've got there. Notice how the bromine and the hydrogen are both shown. Just like in our generic sigma complex, I should get at least one more. Another pi bond moves. The positive charge ends up here, adjacent to the oxygen. And in our generic form, that was it. The charge moves between 3 positions total. But look what I have in this last position. The electron donating group is poised to share electrons with that positive charge. An additional resonance form. Do you know what having additional resonance does to a structure? Stabilizes it. So by having one additional resonance form, this reaction is more stable than if there was not an EDG. Which of these resonance forms is the most stable? Who's got one of our rules for stability of resonance forms? Anybody? What's the number one rule?
Correct charge placement.
Number one rule is not charge placement. The number one rule is not octets. Minimum charges. You want to minimize charges first. Then, octets or charge placement? Octets. And Another way of saying maximize octets is actually maximize bonds to carbon. That's really the only thing we're trying to maximize an octet with. So maximize octets means maximize bonds to carbon, then see if you can place the charge appropriately. Which of these minimizes charges? None of them. Which of these maximizes bonds to carbon? Far right. That's our answer. Despite the fact that it puts the positive charge on oxygen, we are not aiming for appropriate charge placement yet. We are aiming to maximize bonds to carbon. Step 3, if we call step 2 addition, then we can call this step elimination. It does not matter which of your resonance forms you work from here. They all get you to this point. However, I ask that you only use your most previous resonance form. I don't want any doubling up on a resonance form. I don't want you to show this resonance form going to both this one and a different one. Your arrows get cluttered. Some of you have different colors. No. You show one form creating one other form. That's it. Every structure is only related to one other structure. No doubling up. Deal? So if you're doing this fully sequentially, you could have drawn elimination at any of these points, but if this is the last one you've drawn, this is the one you draw elimination from. Deal? Because which of these exists? None of them. So you can draw the last step from any of them, just use the last one you've drawn. No doubling up.
So you don't have like a preference on the most stable one or the least stable, just whichever one?
Correct. Because many questions will even include a bonus maybe that says which of these, if you're drawing a mechanism, which of the sigma complex intermediates was the most stable. That's a whole different learning objective, not draw it from the most stable one. So here's where we're at. We've got this sigma complex intermediate, and we've got this FeBr4 minus. I'm explicitly showing a Br-Fe bond. Despite iron having a negative charge on it, I will not draw this arrow from the negative charge. It's not iron using the electrons, and iron has the negative charge. It is bromine taking the electrons away from iron, alleviating iron of that negative charge. CH bond goes down to form carbon-carbon double bond and breaks open. In this case, breaks open the CO double bond. If it had been here, the CH bond would have just gone in to form a bond. It would have gone in to form a bond and shift a bond. It would have gone in to just form a bond. Different routes depending on what intermediate you have. All right, Killian, you're good with this now?
Mm-hmm.
What I want you guys to do is go through the next 3 or 4 reactions on your sheet, and I want you to do this. Fill in all of the missing charges and this terminology. So notice here, what did you guys add in? When the ring attacks blank to an blank during blank. What did you put? What type of reaction are we looking at in this top one? Bromination, EAS. Those would be the 2 best answers. During bromination, the ring attacks from what position relative to what type of group? What type of group was our OH? EDG or EWG? Electron donating. And how did the ring attack? Ortho to that EDG, meta to that EDG, or para to that EDG? Not ortho and para. In this example, only ortho. But we know that it does both. We're seeing that it's attacking just ortho. What are you going to put on the next one? And that's what I want you guys to do. Fill in these words. Fill in all of the charges. Do that for 1, 2, 3, 4. Don't do the bottom one yet. Just do this for the next 4. Fill in the charges. Fill in the blanks. Name the reaction. Name the group you're looking at. And name the position, the direction that it's going. Okay? Feel free to work together. Collaborate.
For alkylation, do you add your carbon molecule and then an acid?
No.
You can add them together.
Correct.
Do you mean to put a comma between them?
They're just 2 separate reagents. It's not like I'm listing them 1, 2. I listed them, I had a comma because I didn't have them on separate sides of a line. Good. Oh, this is not nitration. You've got an amine, and an amine is not a nitro. But is that the group that's even being added? Yes, it is. How do you know? Correct. Correct. Good. Oh, what do you call this? Amination. You're not adding the amine, actually. Similar to here, what are you adding? The bromine. So what are you adding here? Yes. And we'll call that. It's not methylation. It's making it more generic. I erased it too. Sorry. Alkylation. Good job. These, it's not attacking para to the, this is an electron donating group. This is the electron donating group, ortho, meta, para. So it's actually attacking meta to the group. Okay? But you got your charges right. And then can you name the reaction? So just like here, we were adding bromine. What are we adding here? That's right. Right. So break down into charges. Now let's talk about bromine. So in our top one, we had OH, and the ring attacked bromine ortho to the OH. So when the ring attacks ortho to an electron donating group during bromination, that's our type. Yeah. And you can abbreviate electron donating, EDG, by Russ. Okay. And then this one, we'll just call it O for ortho. Now here, we have another EDG. Notice the bromine is what's getting added in this reaction. Similarly, the methyl is what's being added in this reaction. So this is another EDG. Instead of being an alcohol, it's an amine. So we add another EDG. But is the relationship ortho? Do you know what the position is? Meta. So where a ring attacks meta to an EDG during, and then what do we call it when we add an alkyl group? Alkylation. Yep. Thank you. You bet. Good. And if you can name it more than just EAS, that'll be even better. Can you name what type of EAS you're looking at? Okay. If it helps, focus on your charges first. Those should be the easiest for sure.
Did you finish that reaction?
Oh, I didn't finish it, did I? So close. Do you know how it finishes?
Pi product.
Yeah. You get the orthobromophenol, hydrobromic acid, and the catalyst reforms FeBr3. You should always reform your catalyst. Otherwise, the reaction's not going well.
Can you remove that alcohol?
Not easily, no.
Can expensively remove alcohol.
Maybe.
Less than a liquor license.
Hmm?
Not less than a liquor license.
Not that kind of alcohol. Good. Great. Yes. And you're just working on your charges now? Great. Sure. It's actually not an amide. It's an amine. Mm-hmm. But we can be more generic, and we can just call it EDG. Yeah? And same thing with the one below it. But otherwise, you've got those positions labeled right, which is great. Perfect. Good job. Great. That's great. Good. Looking good so far. Oh, you got a negative there. Yeah, yeah, yeah. Okay, so you go from here to here. But if you move these electrons, you get to this. So it can't be that arrow. What do we need to go from this to this? And the positive charge needs to move over there. Positive charges can't move. Electrons can move. Does it remind you of anything from a plus? Where the electron donating group takes on the double bond. Oh, you didn't add your arrows here either. What do you have on the board? Lone pair from O donates to the C O bond. Creates a CO bond. Right. The only thing I ask is that you draw in that lone pair, and you draw in that lone pair. Thank you. Because otherwise you're showing an atom. You're not showing a person. Good. Now, what charge is on that nitrogen? It just lost something. Good. A reminder, nitrogen with 4 bonds. Positive charge. Yes. I want that to feel like your ABCs. I want you to look at that nitrogen and say, oh, it's bonded just like ammonium. It's got 4 bonds plus positive charge. Good. Now you're going to need an extra number of arrows to go from here to here. You've been using 1 arrow. You're going to need more than that here. Let me see what you got. Okay.
Is it just that this constituent is already there that eventually donates electrons to the resonance? But there's that.
Yes and no. Alkyl groups are also called electron donating, and they don't actually have electrons to donate. Halogens aren't called electron donating, and they do have a lone pair to donate. So it's more about electron donating, electron throwing. It's more about, do you net give electrons to the ring or pull electrons from the ring?
Oh, yeah.
The halogens actually pull electrons from the ring, but can donate in the sigma complex.
Oh, okay. So would they be considered withdrawing groups or
They're neither.
Oh,
Last week we actually put electron donating, electron withdrawing, and halogens.
oh, okay.
They're a third group.
So it would just kind of depend on how well they're able to pull their electrons into the aromatic system.
Yeah, kind of.
Or like, because they don't really like go them all the way to like, if you're like an alkyl group, like the benzene is probably gonna hold on to the electrons.
It's one of the reactions that we talk about have names for those.
Hang on, sorry. The
Remember?
halogen doesn't necessarily want to share its electrons. The alkyl group
But
just
you're
doesn't have anything to
The only
donate.
nitrogen one you're adding.
But the
We're
halogen
not adding the nitrogen.
can donate, and so that helps to stabilize. Halogens are like similar in their
Is it
reactivity
methyl?
to benzenes. They don't
Are you
make
talking
much of
about
a
the last
change,
Oh,
Yeah.
okay.
but they direct
Oh.
orthopara because at those positions they're able to add a new
We're
resonance.
not doing
Oh, okay, so it's really only during the sigma
Catching up.
complex where,
They're donating.
oh, okay.
Correct.
that. He said we need the last.
Good. You bet.
Did he? I totally missed that.
All right, what do you guys think? Should we move on? Should we take a break? Should we go through it together, I mean?
It's the same thing.
Yeah, that's a good idea.
No.
Okay,
Because right on the
second
last one,
reaction.
names the group that was added.
When the ring attacks meta
No.
to an
EDG.
electron donating group, the donating group is the amine, and it's attacking the methyl. We know that because it looks just like the bromine here during alkylation. Good. What do you notice about the number of resonance forms when the ring has attacked meta? There's only 3. So this is not a well-stabilized intermediate. We talked last week about how the comparative levels of benzene, electron withdrawing, and electron donating. Electron donating groups go quickest. I'm going to zoom in now on just the electron donatings because they're not all the same. Electron donating at orthopara sigma complexes versus electron donating at meta sigma complexes. Or electron donating groups cannot stabilize the intermediate if the ring has attacked meta. Why do electron donating groups act as orthopara directors? They activate the orthopara positions to be more nucleophilic. They stabilize the intermediate when it is positioned ortho and para. There are 2 reasons. It makes the ring a better nucleophile there, and it stabilizes the ring. That's what we've got down here. For EAS, electron donating makes positions ortho-para, that's a bit redundant, I'm sorry, makes ortho-para positions better nucleophilic sites. I've even got it here still. And does what to sigma complexes? Stabilizes sigma complexes with extra resonance. Only if it attacks there at those orthopara positions. Yeah? All right, let's look at the third reaction. When the ring attacks ortho, meta, or para. Para to an electron donating or withdrawing? Another donating group. It's another amine. During what type of reaction? Sulfonation here. How many resonance forms? Because at that para-substituted position, the electron donating group is able to stabilize the ring. There's an easier reaction for these orthopara complexes. They are lower in energy with extra resonance. I can tell you electron donating groups are orthopara directors, or I can prove it to you. This is what I'm trying to prove. Are you seeing it, even if it's a little muddy? Let's look at the fourth reaction. When the ring attacks ortho, para, or meta, ortho, which means that we could see the exact same thing that is para, and know that it's going to be similarly stabilized. And it's attacking ortho to what? Electron donating or electron withdrawing? No. Halogen. Halogens are not electron donating groups. They're not electron withdrawing groups. Last week we actually had 3 columns up. Electron donating, electron withdrawing, halogens. Because halogens increase the activation barrier relative to benzene, but they stabilize the sigma complex if it's orthopara. And you can see why the halogen stabilizes the sigma complex. For the same reason that the electron donating groups do. The halogen has a lone pair that when the ring attacks ortho or para, it can share to make an additional resonance form. By the way, if I'm trying to make this graphic a little bit more meaningful, this blue line is pretty much even with just benzene. No electron donating group on it. The electron donating group can't do much to help stabilize the ring better than just benzene alone does. But if we're looking at a halogen, the halogen is still all the way up here. The halogen requires more energy. But again, the halogen is more stable at its ortho-para complex than it is at its meta complex. Don't even see the energy of the meta complex because it's not as stabilized. Halogens are deactivators. They require more energy to run the reaction, but they still stabilize a specific direction. They direct orthopara. What do you see in the last one? This fourth one, second from the bottom, I mean. What type of group is that? The ring attacks ortho, meta, or para? Para to what? To an EDG, an alkyl group, during sulfonation. We didn't name the top one, but this is during chlorination. You know what? I made a mistake because I meant to put acylation on here somewhere, so I apologize for that. What do you notice about this EDG placed para to the nucleophilic site? There's only 3 structures. There's only 3 resonance forms. That's because there is no electron pair for an alkyl group to donate. So then why does it still stabilize the sigma complex better? Why is it an ortho-para director and not meta? Did you place the charges yet? It should be pretty easy. Top right, bottom middle, top left. Where is the most stable resonance form? The middle? Why? Does it minimize charge? No. Does it maximize octets? No. Does it place the charge appropriately? Yes. It places the positive charge on the most substituted carbon. If the alkyl group is meta to the nucleophilic attack, that positive charge can never go on a tertiary carbon. But if the alkyl group is ortho or para, it will always have a tertiary carbocation. That's why the alkyl group stabilizes orthopara. It actually doesn't have the additional resonance like most of our other groups. Yeah? Why don't we take a 5-minute break? Why don't you guys get up and move around a little bit, get your blood flowing, and then I want to come back in and actually look at some more mechanisms.
one is alkylation.
It is nitration.
Here.
No, the bottom one is not nitration. No. You could maybe call it amination.
Ah.
But there is a reason we're not doing it yet. Nitration would be NO2. I guess I put the acylation and nitration on the back. That was silly of me.
Amination. Sulfonation. Why'd you draw the box on the chart? Was it just to say that they're separate?
I just wanted to make those resonance forms a little bit more separate from the structures below.
Resonance.
You're talking about this box?
Oh, sorry. No. This part, it was, you gave us the two options for the reactant.
It wasn't a box. It was two reaction arrows that give you the same product. So if it helps you more, you can look at it like this. It's the same starting material. It's the same product. It's just two different reagents that get you there. I wasn't really sure the best way to lay it out. Maybe I should have done it differently. Maybe I should have just had one arrow and said or. And just gave a second set.
Do you know why alcohol kills germs and stuff?
I think it has something to do with it being a toxin. Alcohol kills your cells too.
So if we were like given the same ratio,
I think so. Yeah. I think that if you were exposed to 90% your weight in ethanol, you'd probably die.
just like being submerged in it for a minute.
Honestly, being around it though, because it just flashes off so much. Wouldn't it? I thought.
Evaporates.
Like it dissipates into surroundings like gas chamber.
But if you were like submerged in it, if you jumped in a tank of hand sanitizer, would you die?
Probably.
Well, one, you wouldn't be able to breathe well. That'd be a limiting factor. Are we suggesting you're inhaling it or not? Because I think germs have different exposure to like their environment than ours.
Do they
Skin
inhale?
cells. We've got like a dermis. Maybe that gives some protection. Your eyes, yeah. So I feel like if you ingested too much of it, you would not survive. Well, you can die from alcohol poisoning. So yeah.
But you have to drink a lot of it.
A lot.
Hand sanitizer wise, you have to drink a lot of hand sanitizer.
But not. But it's non-zero, and it happens.
Oh yeah.
Yeah.
It definitely happens.
And it depends on the alcohol. Obviously, you don't want to like clean your hands with methanol, or you'll die too, even faster.
Well, is that because it like soaks in somehow?
It's more toxic.
Can it
Ethanol
get through your
forms
skin?
acetaldehyde. Yeah,
Which makes acetone in you.
acetaldehyde.
It does not?
No.
Never mind.
Isopropyl alcohol would make acetone if oxidized in you, whereas methanol turns into formaldehyde.
Oh, okay.
And if it gets oxidized further than that, it makes formic acid. And neither of those things are things you want in your body until you're dead and gone. You know,
Want to be preserved?
if you want to.
Do you think? Have you ever smelled almond extract?
Maybe.
You ever made like almond cookies or something?
No. Are you wondering what cyanide smells like?
smells like acetone.
Cyanide?
Yes.
That's
No.
way worse than acid.
Whoa, 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 whoa. Why are you two smelling cyanide?
Well, you
No,
go into
you-
places like embalming places, they will put like cyanide derivatives in here. You might a little like,
Cyanide derivatives.
not actually.
I said
cyanide.
almond
Cyanide
extract. It's
Cyanide smells like almonds.
benzenate?
Cyanide
Benzaldehyde.
itself.
It's benzaldehyde. Bitter almonds. It's benzaldehyde.
Oh, I thought benzaldehyde was cherry flavoring.
Yeah.
Yeah, same.
Yeah. Did you do that in the class?
Mm-hmm.
I should be writing
With a-
my notes.
You know now, right?
I don't know him personally, thank God. Don't want to know him personally.
Why not?
He and I would not be friends.
Why? You don't like his stuff?
No.
Why? Why?
I'm a hater.
Too much information?
I'm a hater.
It seems unfounded.
It is unfounded. That's what haters are.
This is all I studied.
I want to give you guys some more things that are on the bottom of this list. But I could have done a better job at it because it's just kind of all over the place and sporadic. I think rather than trying to go through and give you specific proofs for all of these, we will see the proofs throughout this. But I want you guys to have some of these words. So if you're following along on the sheet, that top row, we already said, was nucleophilic sites and stabilizes. On that second row, electron withdrawing groups make the ortho-para positions worse nucleophilic sites, or less. I think less is probably more grammatically correct. Electron withdrawing groups make those sites less nucleophilic and destabilize sigma complex. They destabilize the sigma complex the least. By the way, these are all mentioning EAS in these top three. And so maybe it would be worthwhile for me to point out that you can do this other part, the electron withdrawing group part at the top on the back. We already mentioned how these electron withdrawing groups have some other double bond in them, and that they can take electrons out into that double bond. So unlike our electron donating groups, our electron withdrawing groups take on a negative charge and place a positive charge in the ring. So you guys can go in and fill those positions. EWG is negative each time. There's a positive charge in the ring. All together, that gives us a similar structure to what we had before, but flipped, where I don't have partial negative character orthopara. My electron withdrawing groups give me partial positive character orthopara. So we're saying that electron withdrawing groups make the ortho positions less nucleophilic. Why would a carbon attack from where it's partial positive? It's going to attack from the part that is more negative. That's meta. Electron withdrawing groups never stabilize our intermediates in EAS. We saw that electron donating groups can share electrons. That stabilizes the positive charge. Donating groups, they don't have electrons to share. They only pull. Electron withdrawing groups destabilize always, but they destabilize the least from the positions that are meta to themselves, from the positions that are their most nucleophilic, or I should say their least electrophilic. And that line on halogens. Halogens make ortho-para positions better nucleophilic sites. I guess up here I was trying to say worse. Less is a good answer there too. But they stabilize the sigma complex at orthopara positions. They're just not as good at making those positions more nucleophilic than electron donating groups.
Why would you say but then?
That's a good question. Why would I put but? Big but, actually. Yeah, I don't know. Sorry, I did make this morning at 8:45, and maybe that was too early in the day to make it. For NAS, if we're looking at those last three lines, things are going to flip. Electron donating groups make the ring incapable. Whoa, now that's a twist. Electron donating groups make the ring incapable of being a nucleophile. Sorry, an electrophile, because it's NAS, the ring has to be attacked. Except for alkyl groups, which become meta-directors. Just like how electron withdrawing groups are bad for EAS, and so they become meta-directors, alkyl groups are bad for NAS, so they also are meta-directors. You'll actually see that at the very last reaction on the front page. That's an NAS reaction, and the alkyl group is meta to the substitution. The negative charge that moves around in this ring, negative charge, has the exact opposite character as the positive charge above it. I don't want that negative charge on the most substituted carbon. I want positive on the most substituted. I want negative on the least substituted. So with NAS, the alkyl group wants to be a meta-director, so it doesn't destabilize the negative charge on a tertiary carbon.
Would that be true for butoxide too?
Any alkyl group. Yep. Electron withdrawing groups, second to last line on the back page, make ortho-para positions better nucleophilic sites for NAS reactions. Huge distinction. It flips on its head. And they stabilize the negatively charged intermediate for NAS with extra resonance. Electron withdrawing groups are to NAS what electron donating groups are to EAS. And then lastly, halogens. Halogens make ortho-para positions better nucleophilic sites, but don't stabilize this position.
So they make them worse?
Thank you. Halogens are not activators for NAS in the same way that EDG is. This is why halogens are their own family. They are just, they're not quite like electron donating groups. They're not quite like electron withdrawing groups. They are kind of their own. All right. So I want to show you guys some more mechanisms that we're going to go through, and we can actually pick some mechanisms that show up on our sheet, and there will be some mechanisms that are not necessarily on our sheet, so we won't look at them. We won't look at specifics for that, anyways. I want to do chlorination, so we can look at the chlorination intermediate that you have on the front page. We're going to take chlorobenzene, react it with Cl2 and AlCl3. We're going to show the formation of orthodichlorobenzene. That's the one we'll show a mechanism for, but there is also a second product form, para-dichlorobenzene. Step 1, formation of the electrophile. Once again, my catalyst and my halogen, elemental halogen, play a role here. My ring does not yet, so I may abbreviate my ring for this step. This looks nearly identical to the bromination, but the halogen and the metal have changed. That's the only difference. Step 2, the addition step. Here is where I have to draw out my aromatic ring, and I have to draw out all of my electrons. I'm gonna, I guess I am keeping up with the sheet that you have. This is how the bonds are placed. Since I'm aiming for showing the ortho group, it's the ortho electrons that need to be taken. Ortho electrons, which chlorine do they attack? Outside or inside? Outside, just like with bromine. Outside chlorine, Cl-Cl bond breaks back to the chlorine. I'm going to draw my catalyst here, AlCl4 in that intermediate. And guess what? We get to draw all of the resonance forms again. So here's a tip. If you know how many resonance forms there will be, you can start by sketching out all of those resonance forms and then just come back later to add in the charges and the arrows. So I know that this is going to have 4 because this is an orthopara director. An orthopara director that is not an alkyl group. So it's going to have a 4th resonance form. On your unit test, you guys know when that is? This weekend. It's due Monday, but you should take it this weekend. On your unit test, you have to show all resonance forms. On your exam, you have to show all resonance forms. So it is good practice to get these forms down. Once you get them down, you can show the bond moving, move the positive charge. Show the bond moving, move the positive charge. Here, we're actually just showing electrons moving, form a positive charge. Remember, you've got these resonance forms on your sheet too, so you can always reference that to make sure that you're placing your atoms in the right spot, your bonds in the right spot. Last step is elimination, just like last time. Where do I start my electron arrow? Not from the chlorine atom. Good. From the aluminum chloride bond. Takes my hydrogen. The CH bond reforms aromaticity. And for this resonance form, that means pushing electrons back to the chlorine. So now we have our byproducts. We've got the orthodichlorobenzene, hydrogen chloride, and our catalyst, AlCl3. Now I want to do alkylation. However, the only alkylation example I gave you on this sheet was when an electron donating group was alkylated meta to itself. How often does that happen? It doesn't really. Ortho and para are the major products of an EDG substituted benzene. So this example that I gave was just to show you that when that group does substitute meta, it can't stabilize it at all. So it's not preferential. So this isn't the mechanism I want to show you, or at least that's not the reaction that I want to show you. Let's take the similar idea though. We'll take aniline, aminobenzene, and rather than working with carbon, just a methyl group, I actually want to show you guys a specific structure. This is called isobutyl chloride, or you can call it 1-chloro-2-methyl-propane. And I want to show you guys this for a specific reason. We'll look at forming the para-substituted product, but I do want you guys to recognize that the ortho-substituted product also forms. We're going to show the formation of para-tert-butyl aniline, where ortho-tert-butyl aniline is also a product that forms. Now I want you to recognize that the carbon my chlorine is attached to is not the carbon that the benzene ring attaches to. There is a rearrangement. That tells you something about the intermediate that we'll find here. We'll find a carbocation intermediate in this mechanism. So I'm actually going to call this step 1A and B, and these will both be the electrophile formation. We'll have an aniline here, but that's not going to do anything in this step. In this first step, chlorine donates electrons to aluminum. familiar. Yeah. Step 1b. We don't have a carbocation yet, so we can't possibly be done. Screwed up. How could I get a carbocation out of that structure? My carbon-chlorine bond has to break. And now I have a primary carbocation, G. Willikers. You know what I mean? Do you know? Do you know how stable a primary carbocation is? Not stable. So for any other alkyl halide, one that does form a stable carbocation, step 1 and step B. That's all that we have for the formation of the electrophile. But I don't have my stable electrophile yet. I have one more step. And here I'm abbreviating AlCl4 rather than ClAlC. ClAlCl3. Just abbreviating it AlCl4. Hydrogen on that tertiary position scoots over with its electrons. This arrow starts at the CH bond because those electrons are moving over. And now I have my activated electrophile. Tert-butyl carbocation. Those 3 steps are just equivalent to this first step. We're just forming the carbocation. That's all that we're doing. Okay, I'm going to come back to the step 2, but I want to show you guys how if my reagents were written as an alkene, this is 2-methyl 2-propene, an alkene in acidic conditions would have given me the exact same process. And in fact, it would have done it in just one step. Alkene attacks the acid. Carbocation always forms on the most substituted position. Boom, done. Activated electrophile is already formed. Are there instances where the alkene addition also goes through carbocation rearrangements? Yes. Just like in OChem1, you can still see carbocation rearrangements. But this is the same exact electrophile. It's the tert-butyl carbocation.
Do they take the same amount of time? Like for us?
They don't necessarily. Yes, I think they would behave probably relatively quickly. And it's really more about what reagent can you get your hands on. That's all. Okay, so either of those methods brings you to this point. I'm going to go back to my original where I had AlCl4- as my catalyst, but I just wanted to point out, you already know this mechanism, acid catalyzed hydration type mechanism. I want you to look at this and figure out where the electrons are going to come from to give me this para-substituted product. Does it come from 1, these pi electrons, 2, these pi electrons on the top left, or 3, these pi electrons on the right? 3? They need to be which carbon's electrons? The paracarbon's electrons. And that means here, electron set 3. Good. Now I have a sigma complex intermediate. Do I know by chance how many resonance forms I'm going to have? What's the minimum? What will you always have no matter what? 3. What do you have when these electron donating groups are stabilizing the intermediate? 4. Unless you have another electron donating group, and then you could have 5, or even another one, and you could get 6. No reason you can't just have as many as you want.
It has to be on the nitrogen, eh?
It will be on the nitrogen, that's right. So we're going to have 4 total. And this time you'll find that the last one is not the doubled up. Or, I'm sorry, it's not where the nitrogen is sharing. I mean, it can be, but it doesn't have to be. All that work, and what have I even done? Just sketched out the forms. I haven't actually added in the electron arrows yet. That's as easy as moving a pi bond, creating a pi bond. Oh, and then this one's fun. I need to restore the lone pair on the nitrogen and move a pi bond. 2 arrows on that second to last form.
Just verifying that group is still a sigma complex, even though we're dealing with.
It is still a sigma complex, totally. Yeah. And our last step, what can we call it?
Addition?
We just did addition. Step 2 is addition. Elimination. Where chlorine takes its bond back from aluminum, bonds to hydrogen, CH bond reforms aromaticity. I get my para-substituted product, my byproduct of HCl, and my catalyst of AlCl3. And that's time. We have one more mechanism in EAS. We're not going to cover nitration or sulfonation. Because they're too hard? No. But just because I want you to focus on these reactions to master these mechanisms. Then we're going to look at the NAS mechanism, which is easier than EAS, in my opinion. So, tomorrow, my goodness, Thursday, Friedel-Crafts acylation mechanism. And then we're going to look at mechanisms of NAS. And then we're going to look at multi-step sequence. How can I bridge these together and take advantage of directing effects to make sure that I get the substituents that I want in the positions I want. All right? You guys did great today. Remember, you can get this online on Canvas. So if you want to try doing it again from memory, go for it. See what you recognize, see what you don't. Get to know those positions, get to know those terms. Thank you for your time. Have a good night.